Damon?
5.
5. I mean, definitely 5 is going to go into 135. Does anybody know what 135 divided by 5 is? 27. And so we keep going as long as we can. What are factors of 27? 3 and 9. And what are factors of 9? 3 and 3. And then all the numbers that are at the bottom of our branches in our factor tree, they can't go any lower, right? They're prime factors, meaning they're only divisible by 1 in themselves. So 3, 3, 3, and 5. Okay, so we're going to concentrate on that. The big difference here is instead of like in our quadratics unit where we were always taking square roots and looking for couples or doubles, now we're taking a cube root. So how many of the same number do we need? We need 3 of the same numbers. Okay, so instead of always looking for pairs now, depending on what the root is, you're going to look for that number of repeats. Okay, so I have 1, 2, 3 3s. So a 3 can go outside my radical. And then instead of doing a square root, I'm going to have a cube root. And any singles or doubles get put back inside. So 5 is the only one left over. Goes inside. So 3 cube root of 5 is the simplest radical form for the cube root of 135. I have one that I would like you to try. So if you would on your papers, do the cube root of 500 for me, and I'll walk around and answer questions if you have them. Okay, so as I walk around, I see a lot of factor trees that started with 5 and 100, and then they went 10 times 10, and 5 times 2, and 5 times 2. And at the end of that, we're looking for groups of 3, and it appears that 5 repeats 3 times, so we can take a 5 outside of the cube root. We're still left with a cube root. And then what are your singles that are left over? 2 and 2. And they don't have enough to go outside, so we have to put all the singles back into the radical, and they get multiplied together. So our final answer should be 5 cube root of 4. Okay? So even if a number appears twice, and it doesn't show up 3 times, enough to come outside, then you have to put all the numbers back under the radical. So 2 times 2 would give me 4. So that's a little bit different than what happened with square roots. How would this process change if I gave you a 4th root? You'd have to have 4 of the same numbers at the bottom of the factor tree, right, in order to bring something out. And if you only had 3, it wouldn't work. It'd already be in simplest radical form. Good. Okay, next thing we want to talk about are 2 properties of radicals for the product and the quotient property. Okay, so the first one we're going to talk about for the property of radicals is the product property. Product goes with what mathematical operation? Sum is addition. Product is the answer to a multiplication, right? Sum for addition, difference for subtraction, product for multiplication, and quotient for division. Now, what's interesting about these 2 products, or these 2 properties for radicals, is they work both ways. Okay? So, I'm going to say that the product property for radicals tells me that the nth root of A times the nth root of B is equal to the nth root of A times B. This means if I have 2 separate radicals that are getting multiplied together, but they have the same root, I could really just put them together, keeping the same root, but multiplying the step underneath. So an example of this could be something like the cube root of 4 times the cube root of 2. If you think about that chart where we have the list of perfect cubes, do you know the cube root of 4? Is 4 in that list? Nope. Do you know the cube root of 2? Is 2 in that list? Nope. So you can't simplify them as they are. Sometimes say, oh, there's 2 cube roots that are getting multiplied together. I'll keep the cube root, and I'll multiply 4 times 2. So that's the cube root of 8, and the cube root of 8 is equal to 2. So you can evaluate it without a calculator, even though, like if we use the calculator to do the cube root of 4, we'd get a decimal answer. Same for cube root of 2. But when we use the property, we get a nice answer there. Now, there's a very similar property for quotients or division. And that property will look something like the nth root of A divided by the nth root of B is equal to the nth root of A divided by B. That was fast.
They took one look at me and then just hired me on the spot.
True story or no?
No.
Okay.
They didn't hire me.
They didn't hire you?
No. I don't need it.
Oh, okay. So you can get a real job out of this? Or no?
Possibly, if
Oh.
they need people.
I see.
Or if they hire like high school students, but most of them don't.
Okay. Note that there's also a statement at the bottom here in red, so I put that in red to make it stand out to you because this is pretty important. This whole rule of like putting things together or breaking things apart as long as you keep the same root, it only applies to multiplication and division. It doesn't work for addition and subtraction. So that's like one of the most common mistakes, that people assume this property translates over into the other operations, and it doesn't. It only works for multiplication, and it only works for division. I'll show you an example of a division one real quick. I'll do the cube root of 24 divided by the cube root of 3. Again, just looking at those cube roots, I don't know those cube roots. I don't know the cube root of 24, and I don't know the cube root of 3. But if I use my quotient property, I can do the cube root of 24 divided by 3, which is again the cube root of 8. And the cube root of 8 is equal to 2. So thinking ahead to your quiz on Tuesday, which you're not allowed to use a calculator for, I could give you a problem like either one of those, where normally we'd say, we need a calculator, we don't know those. But if you use the properties, you'll come up with a nice answer. Yeah, David.
For the division one, what if the number was bigger on the bottom?
If the number was bigger on the bottom, so I'll do one like, the cube root of 2 divided by the cube root of 54. If you're okay with that. And I don't know the cube roots of either of those numbers. So I would put them as the cube root of 2 over 54. And then these are both even, so they reduce by 2. This will be the cube root of 1 over 27. And then to do the cube root of 1 over 27, you might use your quotient property but go the other way. So like now they're underneath one cube root. Just break them apart separately again, now that you've reduced them. So you could call this the cube root of 1 over the cube root of 27. What's the cube root of 1? And what's the cube root of 27? So if the number is bigger on the bottom, then you're likely to end up with a fraction. So that's a good one to see. That uses the quotient property twice. First, I couldn't evaluate either cube root, so I put them underneath to reduce it. And then I could reduce them separately, it's still a fraction, so I broke it up, did the top and the bottom. Good question. Okay, I've got a couple of examples on the next slide, so I'll give you some time, and I'd like you to work them out, and I'll walk around and you can ask me questions if you have them. But think about how you can use the properties from this slide to answer the questions on the next slide. Okay, I'm seeing some very good work as I walk around the room. Most people on the very first one use their product property to do 2 times 12 and get the square root of 24. And then just remember, your answer should be in simplest radical form. So maybe run through the factor tree. And then pay attention to the index, because this is a square root. We need pairs, doubles, or groups of 2. So we've got 1, 2 that comes on the outside, and then we'll have a square root of 2 times 3, the singles left over. So then 2 square root of 6 would be our final answer. Okay, but as I walked around, most of you were able to get that, so good job. On the second one, some people got out their calculators because they're working with a little bit larger number, but they used their quotient property to divide 192 divided by 6 underneath the 5th root. And what do we get for that? Just say it out loud. 32, thanks a lot. Okay. And the 5th root of 32 is 2. How many people know the 5th root of 32 now? Just from like doing the homework assignment and looking at the chart during flashcards. I mean, like, this is the thing. You're going to do the 5th root of 32 a lot because it comes out nicely. And then eventually you're going to walk away saying, I know the 5th root of 32 is 2. Until that point, continue to look at your chart and get familiar with some of those numbers. But the smaller ones, you'll get better and better at as we use them more often. But yeah, that works out nicely to be 2. Great. Any questions or clarifications that we need to make about product or quotient properties? Always remember those properties go both ways. You can put stuff together or you can take stuff apart, but it doesn't apply to addition or subtraction. Okay, so those are 2 important ideas. Last thing we want to talk about is adding and subtracting radicals. And so here are a couple of notes to make about adding and subtracting radicals. Definitely have covered this before in Algebra 1. You know, adding and subtracting in math is always a matter of combining like terms. Every time. Even when you're adding and subtracting numbers, 5 plus 3. Those are like terms. So you add them together and get 8. Okay. Then I can give you like polynomial expressions from chapter 4. And I could give you something like x cubed plus 2x squared plus 1 plus 4x cubed plus 2x plus 3. And you just group your like terms and add the like terms, right? So nothing changes in addition and subtractions with radicals. It's still our objective, as it always is in math, to combine like terms. And how we'll decide if things are like terms is if the radicals are exactly alike. So the radicals must have exactly the same index, so it must be the same root, and they must have exactly the same radicand. I always tell a funny story, and funny is more like weird, okay? But this is how I tell people to imagine this, so that you can think about this on your own later when you see a radical again. Suppose you're at Walmart, and Walmart sells radicals. Wouldn't that be awesome? Aisles and aisles of different kinds of radicals. Cool. Okay. And you got your cart, and you're going down aisle 7, and you stop and you look to your right, and you're like, oh, cube roots of 5. I needed some of those. So you take 3 cube roots of 5 off of the shelf, and you put them into your cart. How many cube roots of 5 did I put in my cart?
3.
3. Okay. Then I keep walking down the aisle, and then I'm like, wait a minute. You could never have too many cube roots of 5. I better go back and get some more. They're on sale. Why not? Okay, so I go back to the cube roots of 5, and I grab 2 more cube roots of 5, and put them in my cart. How many cube roots of 5 are now in my cart? 5 cube roots of 5. Okay. Did the cube roots of 5 turn into anything else when I added more into the cart?
No.
No. So adding and subtracting things in math doesn't change what they are. They don't become 6 roots of 10, and cube roots of 10, and 6 roots of 5, and things like that. You leave the radical alone, and you just count up how many you have. So if you can imagine that story, every time you have to add or subtract radicals in the future, you'll never have any trouble again. Good story, right? It's so silent. Just let that marinate for a day. Then you can come back and tell me what a great story it was. Don't even smile. I don't even want you to smile. Okay? There are no smiles allowed. Don't have any kind of fun or enjoyment in this class ever, please. A 4 through to 10 plus 7 4 through to 10. How many 4 through to 10s are there? 8. The leading coefficient to that very first 4 through to 10 is, there must be like a 1 there. And so all you're doing is adding 1 plus 7, and you're getting 8 4 through to 10. Okay. Notice, not 8 through to 20. Nothing happens with the radical. That is just a thing that gets added. Okay. I could buy 4 through to 10 at Walmart. I don't always have to have them looking like radicals because we now know they can look like rational exponents. So I could apply this to rational exponents too. I have 2 8 to the 1/5 plus 10 8 to the 1/5. How many 8 to the 1/5 are there? 12 8 to the 1/5. Notice they do not become 16 to the 1/5 or 16 to the 2/5. There's no other addition and subtraction other than how many of those things I have. So remember, in math, you have to decide what are the things that you're adding. Okay, and keep the things as they are. And one final one is a cube root of 54 minus a cube root of 2. Cube root of 54 minus a cube root of 2. I think it might be hard for all of us to see, so I'll write it up here. Cube root of 54 minus cube root of 2. What do you instantly think there? You can't subtract them because they're not the same radicand, right? One has 54 underneath and one has 2. They're in totally different aisles at Walmart. And they are not at the same. Okay, they ring up differently, for sure. Before you scratch this problem and just say cannot do, what might you do? Yeah, simplify it. You might do the factor tree on them to see if they are still somehow like terms. So I would look with the bigger number here, 54. What are some factors of 54? 9 and 6, cool. 3 and 3, 3 and 2. And since we're taking a cube root of 54, we need a group of 3 numbers. Got it. And then I'm going to still have a cube root of 2 left over. So the cube root of 54 is really 3 cube roots of 2. Can you subtract now? 3 cube roots of 2 minus a cube root of 2. How many cube roots of 2 do you have? 2. So before you give up and say, nope, can't do it, I would like to see you do the simplest radical form. Is it possible that they simplify and you still can't do it?
Yes.
I think so. I think that would be allowed. Okay, so don't be alarmed if you're like definitely positively getting ones that don't add or subtract, but just make sure that you've checked that. Everyone